All right. So so I'll be talking about how we can constrain dark matter properties from the inner structures of dark matter halos. Um, so we've heard a lot of introduction about what dark matter halos are, and essentially we are currently at a stage where there are multiple lines of evidence about the existence of dark matter. Um, right from the beginning, from rotation curves to to virialized clusters, to galaxies and clusters, to the existence of disks, and in more recent times, the CMB, the large-scale structure, strong lensing bullet cluster. So we have various, so it's a really robust model, and moving away from it will take significant effort. So while we now understand that a universe, the matter component of the universe has to be largely dominated by this dark component, because this dark component gravitates, and we expect the largest overdensities of dark matter to exist in these structures that we've been talking about in this session, particularly called dark matter halos. So dark matter halos are basically endpoints of structure formation, and they are the potential wells within which all of the galaxy formation takes place. So that's the standard model of galaxy formation and structure formation that we think about. So dark matter halos have been studied quite extensively through n-body simulations, particularly the standard paradigm, right, which has been very successful in explaining the large-scale structure of the universe. The standard paradigm of having cold, collisionless, cold, non-relativistic collisionless dark matter has been tested quite well and has been studied quite extensively. So even in the standard cold dark matter scenario, where by cold we mean that dark matter does not have significant thermal velocity, its bulk velocity dominates any thermal velocities. The inner structures of dark matter halos can have very rich phenomenology, as we've been studying. We understand that the structures of these dark matter halos, particularly as studied through simulations, have show universal behavior. We also understand that in the cold dark matter universe, where structure is seeded through perturbations, you expect to have the smallest overdensities collapse into gravitational nonlinear structures. So you expect hierarchical structure formation. So each of these dark matter halos have hierarchy of smaller substructures within them. But over time, this structure of dark matter halo we also understand now in more detail, even when we want to test out completely the cold dark matter paradigm, there are actually many even more beautiful things that we can really start to study when we start studying the inner structures of these dark matter halos. For example, we have this idea that dark matter halos, so this is the density profile of a dark matter halo, this is the slope, the density, a logarithmic density slope as a function of radius, and we expect it to be most halos to look like NFW, where it goes to -1 in the inner region, and the logarithmic fall off hits -3, which is this profile over here, dot dash. But now we understand that particularly near the outer regions of the halo, there is actually a significant departure from this behavior, and all of these different behavior are actually sourced and can be seen beautifully when you go ahead and look into the phase space structure. If you see the velocity and the radius structure of dark matter halos, you start to see many more different structures, which you can actually go out and try to test in the universe. All right, so I will not talk about particularly the cold dark matter scenario. I will talk about, or rather I will not focus on these specific structures today. What I want to really talk about is how, while on large scales, cold dark matter has been a very successful model to explain the clustering of galaxies on large scales. On smaller scales, when we really go and test these regions of high overdensity of dark matter, there have been some significant challenges to this cold dark matter scenario, right? And these challenges have come up from observations, with our observations getting really, really sophisticated over the past few decades, right? Some of which is, of course, these are well known, and I'll just state them, and over the past 2 decades, many of these have evolved. So the standard issues that we talk about are, of course, the core cusp problem. When people went out and measured the stellar velocity profiles of dwarf galaxies, they saw that most of these dwarf galaxies, instead of having a cusp, right, where you expect the dark matter to steepen towards the inner regions of the halo to a -1 NFW-like slope, most of these dwarf galaxies show a shallower, most of the classical dwarf galaxies show a shallower cored region. Other than that, we went and counted the satellites, the satellite galaxies of our Milky Way, which we think live inside, their own dark matter halos and are substructure in the larger Milky Way halo. We found that there was a large missing satellite problem, that CDM theory, cold dark matter theory, predicted many more satellites compared to what we were observing in the universe. And then there was also the too big to fail problem, essentially that the brightest satellites that you saw in the universe, if we imagine that they should be living in the most massive satellites of CDM halos, they should have had much larger circular velocities. So somehow the largest circular velocity halos in CDM simulations don't seem to be hosting galaxies. So that's the too big to fail problem. So these problems have existed for a while. They have now been reframed, I would say, rather than firstly, I'll just go into what is the new framing of some of these old problems. So it's like a status update. So essentially what is happening is this, the missing satellite problem to start with is no longer considered a tension anymore. And this has largely been attributed to better observations, finding fainter galaxies in the Milky Way. And as a matter of census, it appears that we don't have, just if we were to count the numbers of galaxies, it appears that at least in the Milky Way, we don't appear to have this missing satellite problem anymore. The core cusp problem, now that we can measure not only a handful of classical dwarfs, we can actually measure a large tens and 50 or 60 dwarfs going to fainter and fainter regime. The core cusp problem has also been recast to a large extent. In fact, now we don't only see cores in galaxy, satellite galaxy halos, we actually see a diversity of rotation curves. Okay, so the scatter, so the entire spread of rotation curves of galaxies from dwarf satellites and nearby galaxies is much larger, is still significantly larger than what we actually expect in CDM. So the core cusp problem one can think of has been transferred into this diversity of rotation curve problem. And finally, I think even though the census of number of galaxies is more or less resolved, I think the relationship of how stars populate dark matter halos is still not well understood. Okay, so the stellar mass halo mass relationship, the relationship of star formation rate to these faint satellite galaxies or halos is still not a solved problem. We still don't completely understand how to go from a CDM universe to explain the stellar mass halo mass relation or the diversity of rotation curves that we see in the real universe. Okay, so particularly a lot of these problems were, a lot of these classical problems had motivated models of dark matter that essentially in some sense tended to suppress structure formation, suppress clustering in some sense, right? So in particular, we think that there's a potential well, CDM being non-relativistic and cold would just collapse into these potential wells. But if CDM had a lighter mass, had thermal velocities, or if these CDM particles had other ways of exchanging energies, these bulk flows would then we could be able to disperse out dark matter particles from these deep potential wells, creating essentially shallower halos in shallower cores, or disrupting away satellites essentially, right? We wouldn't collapse to the smallest objects. So while these were original motivations for thinking of many of these models, we actually, going ahead, while some of these motivations have been recast, I think it's still interesting to go ahead and ask, what do these dark matter structure, the internal structures of dark matter halos actually, what kind of constraints do they put in the different do they put on the particle properties of dark matter, right? So we can still go and ask just from motivation from particle physics side, like how do these profiles actually constrain the different properties of particle dark matter or wave dark matter. All right, so I have particularly with collaborators, we've been working quite extensively on self-interacting dark matter. So unlike in cold dark matter, where dark matter can only interact gravitationally, self-interacting dark matter are essentially dark matter particles that are allowed to have some interactions with themselves beyond gravity, right? So what this essentially does is, because the particles can interact with each other, it gives them a channel to exchange momentum. It gives them an additional channel to exchange momentum with each other. So it can redistribute the energy of the particles, and therefore it predicts a significantly different internal structure, the dynamics of dark matter particles in these dense regions have significantly produced significantly different structures. So mostly we understand that self-interacting dark matter tend to form cores at the center of halos. And this is particularly because if you have an NFW-like CDM halo, or if you have dark matter gravitationally bound structure, the internal velocity structure looks something like this black line. And what self-interaction does is transfers heat from this hotter region to the inner cold regions of the dark matter halo. So that essentially tells you that it heats up the inner regions of the halo, basically allowing particles to escape from the inner core of the halo. So not only does it escape from the inner core of the halo, it also makes the profile steeper in the outer region. While this was the standard picture, we also understand that while coring is the first phase of dark matter evolution in the self-interacting halos, what actually happens is, if you allow for self-interaction, and if you allow for large enough self-interaction, after the stage of thermalization of the halo, if you have too many self-interactions, these halos actually eventually tend to evolve I'm doing really bad on time, tend to evolve to core collapse structures. So what essentially happens is that once you thermalize the inner part of the halo, and because of this thermalization, if the hottest particles tend to escape, the core actually tends to collapse to reaffirm virialization. So it's a negative heat capacity problem in gravity. And as the core shrinks to a smaller radius, it then settles down to a wider velocity distribution, hence losing even more hotter particles, and eventually this becomes a catastrophic process leading to the collapse of the halo core. Okay, so essentially what happens is it's a competition between two time scales, your local dynamical time scale to the interaction time scale. So all self-interacting dark matter halos are in fact expected to core collapse at some point of time. So you form a core initially, but eventually if you have too many interactions per orbit, you actually start to become much steeper than even the NFW profile. So you expect a core forming phase, and then you eventually go into this core collapse phase. So essentially, what was well known is that while this has been known that SIDM halo should core collapse, typically the time scales for core collapse have been much larger than Hubble time, given the densities of dark matter that we expect in the universe. However, recently it's been pointed out that in tidal environments, if you have satellites of satellites of large galaxies, the outer part of the halo becomes colder because of tidal stripping. You can actually start the opposite transfer of heat much faster, and you can really start to core collapse in cosmological timescales. Not only do you have this when you have elastic interactions, this additional channel of heat loss is even important if you move away from elastic scattering, like I'll take 2 minutes, situations, and move it to dissipative dark matter self-interactions. Then also you start to core collapse. So right. So basically the distribution of dark matter in halos encodes various types of, a rich phenomenology of structure inside of it, right? Whether you're forming core collapse, you can, where you're cores or your cusp or your collapse, these different stages of halo evolution can be tested by a variety of observations that we can look into. I'll just take 2 extra minutes. Where are we right now? So this is the typical expectation for elastic scattering. So on the x-axis here is the interaction cross-section times v, and this is the velocity scale, so the halo mass scale. So typically on cluster mass scales, the most robust constraints are these bullet cluster constraints, which are of the order of 1 to 2 centimeters square per gram. And on the dwarf scales, you can essentially have much higher cross sections. In particular, what we've been working on there are various intriguing observations that hint at something strange happening on both the inner, particularly in the dwarf scales, which I will not go into today. In particular, people are now, instead of finding core cusp halos, there's been an evidence of finding a substructure in a strong lens system, which is about almost 4 sigma away from an expected subhalo in a CDM universe. What we have been working on recently is on cluster scales. Can we put better constraints on the dark matter self-interactions on these massive cluster scales? So in particular, most of the cluster studies have been focused on measuring the cores of dark matter halos, right? The sizes of the cores. But if you look at a galaxy cluster, this is a 2 megaparsec size, roughly galaxy cluster. The studies that test SIDM are basically strong lensing studies that are measuring the dark matter mass in these regions. And of course, in these regions, there's a massive galaxy sitting over there. So a lot of the very stringent constraints that come on cluster scales are thought to be contaminated by these massive galaxies sitting there. But what we have been looking at recently are these galaxy clusters and trying to understand whether we can get constraints on these dark matter particles from the entire profile of the dark matter halo. So we've been measuring these dark matter distributions from weak gravitational lensing in galaxy clusters. And essentially, while the strong lensing probes this part, weak gravitational lensing, which measures this excess surface density, probes a much larger region of the dark matter halo. So what we've been finding essentially is that there are some subtle discrepancies from a CDM expectation, which is this black dashed line over here, particularly in the inner parts of the halo. So we've been using these slope profiles to constrain dark matter density distribution. Given how good weak lensing measurements are today, we are essentially trying to use these measurements to distinguish between different dark matter models. So what we are really trying to measure is this region. So as we have some part of the core in the outer regions of the dark matter SIDM core, but we are also seeing this steepening over here, and our weak lensing studies are becoming so accurate now that essentially we can, while the matter is pushed out of the core and it accumulates here in the outer region, current lensing surveys can really start to distinguish between these models. So in a recent study, what we've been doing is we've been using these lensing profiles and comparing these models to these dark matter only, to these SIDM self-interacting dark matter simulations. And for the first time, we've used the entire profile of the dark matter halo, starting from the scale radius to the virial radius, to put constraints on the self-interacting elastic dark matter interaction cross-section. And our constraints are competitive with the bullet cluster constraints currently, which is of the order of less than 1 centimeter square per gram. And we've also gone ahead and actually, instead of elastic scattering, if you had dissipative scattering, you would actually start to make the profile much steeper than CDM. So you could also start putting constraints on these dissipative dark matter core collapsed models, even on cluster scales, using the entire profile of the halo from the scale radius to the virial radius. So we use these measurements to put novel constraints on these dissipative dark matter models. And while currently, even with DES year 3 data, our models are already competitive with a bullet cluster-like constraint. With a survey like LSST, our current constraints just from the outer part of the halo, outside of 0.2 megaparsec, which is at the edge of the core of the SIDM, if these are our current constraints, with a survey like LSST, our constraints will become really, really strong. I'll finish essentially with that essentially, given a vast range of phenomenology which is now being looked into and the power of current data, we can really start to be creative about what are the different ways in which we can test dark matter. And I just wanted to talk about this small work where we have used not just focused on the core, but essentially the entire structure of the dark matter halo to put some first constraints on these cross sections. Thank you. I'll stop.
Yeah. A very quick, only one question. Another person, just start.
So my question is that these self interactions, repulsive or attractive doesn't matter. It's depends only on that cross section. Is it true?
Yes. So we don't go into the microphysics. So essentially, yeah, it only depends on the cross section and how much energy you.
So another quick question is that, so in this type of self interacting model, so you only considered these elastic scatterings, but there can be some 3 to 2 scattering that two dark matter can go to 3 to 2. 3 to 2 processes can occur. So in that case, how these results change?
Yeah.
Do you have any
So I've spoken about both elastic scattering and these kind of dissipative scattering where you might have two different dark matter microstates that are slightly separated in mass. And you can actually lose net energy.
So I'm actually talking about the single component.
Okay.
Seems like dark matter where this 3 to 2 process happens. Okay.
You can tell me about it. The microphysics.
Yeah.